You notice your breathing? It's repetitive. Because if you stopped breathing, well, then all things would not work too well. So our breathing function follows a repetitive model. So let's look at how we're going to learn to model some periodic behavior. This graph that I drew is basically a graph of your air velocity where it's positive on your inhale and negative on your exhale. And that complete cycle in this particular model takes 5 seconds, where the total velocity, the amplitude, would equal 0.6 liters per second. So based on that information, are we able to develop the model that created this graph? Can we develop our function? Well, we know the basic function. This looks like a sine graph. Starts at 0 and continues on. Could be a cosine graph as well with a phase shift, but basically it's a sine graph. It has an amplitude, but also has a period as well. There's no phase shift since it starts here right at 0, 0. So do we have enough information to develop the equation that represents this graph? Can we do this problem backwards? Well, sure we can. Amplitude is 0.6. Done. That was good. But how do we find the value of b? Well, do you remember the value of b was where we took the value over the period. The period in this particular case was 2 pi of a total sine graph, and we divided it by the value of b. So if we started with this is what our next step would be. Well, we discovered that this full period is 5 seconds. And now what I want to do is just simply solve for b. And this would become b equals 2 pi fifths. So now I have all my variables taken care of. The model or the function that produces this graphical representation is a graph of y equals a, which is 0.6, sine. My b was 2 pi over 5 times x. If I were to graph that, this is what I produced. Now that I have produced this, can I work backwards and fill in the values? Yes, we can. We just did. All right, let's have some fun with this one. Imagine you're on a boat, and there's some of the things you know about that boat because you are aware of, and this is in the ocean, and you're aware of tidal waves. Or not tidal waves, but we have tides where the water comes in, the water goes out. Well, on this particular day, we noticed that at 4 a.m. in the morning, the bottom numbers here represent hours past midnight. So at 4 in the morning, we have a low tide. It's registered at 5 feet. At 10 o'clock that day, or 10 hours past midnight, we have a high tide. And then we have a pattern that continues as we go from there. So based on this information, can we develop what the model is? Based on some y equals a times sine bx minus c plus a d. Do you remember what a, b, c, and d all represent? And can we get that from this model? So let's begin. So I'm going to just start with y equals a times sine bx minus c plus a d. Well, our amplitude, which is our a, we might be able to find that one fairly straightforward. Their amplitude is from the middle of the graph. How far above and below does it go? Well, the middle of our graph is at 9, and it goes up to 13 or down to 5. So the amplitude would be a 4. All right, not bad. D might be the next part that might be fairly easy for us to kind of figure out. That was its vertical shift. This middle point at 9, well, that's 9 feet above 0. So my vertical shift, or my D, would equal 9. So far, I have a graph that equals y equals 4 times the sine of bx minus c plus a vertical shift of 9. All right, that was just kind of cherry picking some of the low-hanging fruit there. So let's figure out how we get b. Well, b was representing by our period. And we remember that b equals 2 pi divided by whatever that measurement was. Whoops, sorry. divided by b. And that value became our starting point or ending part of the graph. So let's look, since this is a sine graph, let's start right here because our sine usually starts at the baseline and continues up. Let's use from those 2 points as our full cycle there. Tells me then at this point is halfway between 4 and 10, which is a 7, and the ending point is halfway between 16 and 22, which is 19. So during that full period, what's our measurement? Well, it's the time it took go from 7 to 19. So 19 take away 7 is a 12. I can solve that and now solve that for b. b equals 2 pi over 12, and that equals pi 6. All right, so I can add that to my equation if I want. So let's make that y equals 4 times sine, pi is b6, or b is pi 6, x minus c plus 9. Now what we don't have is our phase shift. Now remember phase shift? That was our ratio of c over b. And in this particular case, our phase shift moves the graph over and it starts at 7, because that's where the sine function, all in between there that I have in blue, represents one complete sine movement. So it starts at 7. I already know what b is, so that'd be 7 equals c divided by b, which was pi 6. Solve that for c, so multiply both sides by pi 6, and I get c equals 7 pi 6. Last piece of information I needed, so I have all of the pieces. So my complete model would be y equals 4 the amplitude times sine. B was pi over 6 x minus my phase shift, which was 7 pi 6. Plus my vertical shift. We were able to do all of that based on just this, what appears to be limited information. So a lot of modeling requires for us to see what information is available and then just slowly, bit by bit, work our way backwards so we can come up with a graph or the equation that produced that information. It's kind of fun.